Hello and welcome to LFI Educates. Today we are going to start this chapter in physics, chapter 12, that is atoms. In this chapter, basically we will be focusing on the structure or the model of the atom. In the beginning, the first thing that you are going to study is about alpha particle scattering experiment by Rutherford. Then the next thing that you are going to study is about the postulates given by Rutherford about the structure of the atom, Rutherford's model of the atom. Then the third thing that you are going to learn in this chapter is about the electron orbits, how electron revolves around the nucleus. Then the drawbacks of Rutherford's model will come. After that, Niels Bohr in 1913 gave the structure of the atom and study about the basic postulates of Bohr's model of the atom. Then we'll study about his theory of hydrogen-like atoms given by Niels Bohr. Hydrogen atoms or hydrogen-like atoms, like ions of helium as well as ions of lithium. These are also applicable. Then in the sixth step, we'll study about the hydrogen spectrum. And then we'll learn the energy level diagrams. From Bohr's point of view, here you have to focus more from here, the basic postulate of Bohr's model of the atom and the theory of hydrogen or hydrogen-like atoms. Here most of the time questions comes from this portion. Now regarding atoms, when we say atoms in olden days, people are believing that it is indivisible. That's how the name is also derived, atoms. The meaning of the word atom is indivisible. They are the building blocks of all matter, this is correct. But after the discovery of electrons by J.J. Thomson, then the discovery of neutrons by Chadwick, discovery of protons goes in the name of this famous person, Rutherford. The first person to present the model of the atom was J.J. Thomson. According to his model, in lower grades you have already studied, you are very familiar with it. It's called watermelon model of the atom, or we call it as the palm pudding model of the atom. He considered the electrons like the seeds of the watermelon. These are the electrons. And the integral part that he considered as the protons. But this theory failed because when heat is produced on the surface of metal, then we know that electrons only comes out. The protons does not come out. That was the major drawback of J.J. Thomson's model of the atom. He was unable to explain even the ions and the ionic compounds in chemistry, how they are formed, and that was the major drawback of this Thomson's model of the atom. Now to start with this chapter, we will be doing this alpha particle scattering experiment, the discovery of the nucleus and the position of proton. Proton is present in the nucleus of an atom. at the central core of the atom, and the whole mass of the atom is concentrated at the central core. That we call it as nucleus. Now let us begin with alpha particle scattering experiment performed by Rutherford. Alpha particle scattering experiment by Rutherford. The experimental setup was made like this. A lid cavity, so that the harmful radiations that comes out will not be spread in other direction. Lid cavity. Bismuth, atomic number 83 and mass number around 214, was taken as the source of alpha particle. It was taken here as a source of alpha particle. Then a slit type of structure, we call it as collimator. So that the alpha rays that will come out from here will go in a single straight line. Next to that, he took a gold foil in a stand. Gold is chosen so that gold is the most malleable metals we know. You can beat them into thin sheets. Compared to any other metal, gold is the most malleable metal. It is of the order of, exact value is around 2.1 into 10 to the power minus 7 meter, or we call it as, in the order form, if we write 10 to the power minus 8 meter also we say. Gold foil, this is your gold foil. It is taken, and then these alpha particles were allowed to go and hit the gold foil. Now after hitting the gold foil, there was a screen made up of zinc sulfide. Now if I draw, it will be around from here, around like this, it will be taken. But if I draw a part of it, I'll draw this way. In a circular form, it is taken. And then this is zinc sulfide screen. These alpha particles, after striking the gold foil, they went in different direction after striking. And how many of them went straight? How many of them went at a certain angle? To detect it, one microscope, a rotatable microscope, is used as a detector. This microscope, you can rotate around the screen like this. All around you can move. This is zinc sulfide screen. How you come to know that how many of them went and strike the zinc sulfide screen in the straight direction? The scintillations will be produced. When alpha particle after striking the gold foil will go and hit there, like a spark, tiny sparks will be produced. Most of them were found to go straight. They came like this. Some few, if I take this as a straight line, some few they were deflected at some angle. This is called a scattering angle. We are marking it as theta. And one out of around 8,000 scintillations that are produced on the screen, they were deflected back. They were deflected back. The deflection at 180-degree angle. Deflection at 180-degree angle. These were the observations made by Rutherford in his famous experiment, alpha ray scattering experiment. Now let us see the observations made by Rutherford. Observations that are made from this experiment. The first one, most of the alpha particles that strike the gold foil, they went straight. Most of them, they went undeflected. Most of the alpha particles passed straight without any deflection. Then the second point, the large number of alpha particles were deflected at different angles theta, the angle of scattering. Some were deflected like this, some were deflected this way, some were deflected like this, some were deflected this way. So large number of alpha particles were deflected at different angles. Between 0 degree to 180 degree. Between 0 degree to 180 degree, a lot of alpha particles were deflected at different angles. Between 0 degree to 180 degree. That was the second observation. Then the third observation was that 1 out of 8,000, say, they were deflected at an angle of 180 degree. They were deflected back. The third observation, 1 out of around 8,000 particles were deflected at an angle of 180 degree. That was the third observation. That means 1 out of 8,000, then you can just think very less of them they are deflected back at an angle of 180 degree. This angle will form 180 degree. That means going and returning back to the same path. And the fourth point, what was observed is the number of alpha particles deflected at different angles. If you plot it in the graph, graphically you can show the number of alpha particles and the angle of scattering is shown graphically like this. We'll draw one graph to study the number of alpha particles and the angle of scattering. Number of alpha particles scattered. If I plot it this side, number of alpha particles scattered. If I write this n theta, and suppose say 10, 10 power 1, 10 power 2, 10 power 3, 10 power 4, 10 power 5, 10 power 6, 10 power 7 and so on. And suppose here if I start with 0, this angle theta, angle of deflection theta along x-axis, 0, say 20 degree, 40 degree, 60 degree, 80 degree, 100 degree, 120 degree, 140 degree, 160 degree, 180 degree. Then a nature of this curve was seen this way. That means at less angle, more alpha particles they have passed. Number of alpha particles were more. As the angle is becoming more and more, number of alpha particles scattering has become lesser and lesser. And when the angle became 180 degree, the number of alpha particles scattered became the least. It shows like this. So these are the following observations made by Rutherford. Before proceeding further to the conclusions made by Rutherford, let us know about this alpha particle little bit. You may be thinking, what is alpha particle? What is alpha particle? Alpha particles are doubly charged helium nucleus. It contains +2 charge and they assemble to helium atom. This is your alpha particle. They are produced during alpha decay. The topic is removed because of the lockdown, alpha decay, that you are going to study in the next chapter. This is 12, the next one is chapter 13. But let me tell you about this alpha decay. In heavy unstable nucleus, bismuth we have taken 83, bismuth 214, more than 210. What happens to them is, if they are exposed, then the short range nuclear force which is holding them becomes too weak to overcome the repulsive force of the nucleus, that is helium nucleus, and the nucleus of the atom. So what happens, let me write this X. This is your bismuth, suppose. This atomic number we write as Z and mass number we write as A. During this alpha decay, they release, the mass number gets reduced by 4 and the atomic number gets reduced by 2. Suppose this is a new product will be formed. Along with that, you get this helium nucleus. If you add up A minus 4 plus 4 is A, Z minus 2 plus 2 is Z. And this helium nucleus, we are calling it as alpha decay. We are calling it as alpha particle. It contains 2 charge, +2 charge. This one will indicate the charge, and mass, as you can see, it is 4. This is your alpha particle. It is heavy in nature. It cannot travel more in air. Certain distance on it can travel, but if they come in contact with matter, they can produce a large effect on it, or heavy contact can take place with matter if it comes in contact. That is your alpha particle. Please try to remember, alpha particles are doubly charged helium nucleus. They carry 2 electrons and they carry 2 protons. They carry 2 electrons and 2 protons. Their charge is +2 and they resemble your helium atom 2He4. These particles we call it as alpha particles. Then we will discuss about now the conclusions made by Rutherford. Now let us see the conclusions made by Rutherford. The first point is most of the particles went undeviated, they went straight. It indicates that an atom has a lot of empty space in it. Like suppose if I draw a nuclear model now, this is your nucleus. This is your suppose electron orbit. And most of the alpha particles they went straight. That indicates an atom has lot of empty space. That is the first point. The second point is that 1 out of 8,000, as we have said, they go and come back to the same path, making an angle of 180 degrees. They come back along the same path, indicates that the entire mass of the atom is located at the center core called the nucleus. The entire mass and the entire positive charge, everything is concentrated at the center of the atom, because we know that alpha particles are heavy particles. But if they go and strike there, still it gets repelled back. In a small region, it is still going and repelling back. That indicates that this mass is much more higher than the alpha particles. Alpha particle itself is not very light, it's heavy, but still then it can go and bounce back. That means this is much more heavier. The mass or the mass of the central core of the atom is very heavy. That was concluded. Let us see the third point. The third point says that as the rays went nearer to alpha particle towards the nucleus, towards the central core, the deflection angle became larger and larger. As it comes nearer, the angle becomes larger. If you go away from it, then the deflection angle is a little bit less. This deflection angle is less, but if you come nearer, deflection angle becomes more and more. Now this deflection angle was explained by using Coulomb's force between two charged particles. Alpha particles are also positively charged. The nucleus is also positively charged. So Coulomb's law of electrostatic, if you use, this is 1 by 4 pi epsilon naught 2 times E, that is the charge of alpha particle, and ZE we write for the charge of nucleus, divided by the distance square, that is R square, or if you write this as an electrical constant K, then you can write it as 2E into ZE divided by R square, the distance of alpha particle from the nucleus. That gives us the force of repulsion. It is to be remembered that it is not a force of attraction, it is force of repulsion. They are repelled. This way they are repelled. That's how the conclusions were made. Thank you and have a nice day.